In this video, I'm going to go over the IRA tab. So again, we always want to begin by carefully reading the research description. So ours reads, historically, the average market rate of return for Roth IRAs is 8.6% with a standard deviation of 1.7%. An analyst takes a sample of Roth IRA accounts at Vanguard and observes their rate of return for the past 10 years. Conduct the appropriate hypothesis test to determine if the Vanguard accounts have a different average rate of return in comparison to the historical market average. Set alpha at 0.05%. All right, so this is a one sample z-test. And the reason why is because we have a sample and we are comparing it to a population mean. And we know the population standard deviation. So that was provided to us. So again, with these one sample tests, we have one sample and we are comparing it to a population mean. So we have a sample of accounts at Vanguard. So Vanguard is our sample. And we are comparing Vanguard to the historical average market rate. So the population mean is the historical average. So the next one is whether it's left, right, or two-tailed. Now remember, this depends on the alternative hypothesis. So this is the same as the alternative hypothesis. We are just looking to see if Vanguard counts have a different average rate of return. So this is a two-tailed test. So one-tailed left is if we would think that or hypothesize that Vanguard has a higher rate of return. It would be a one-tailed left if we had hypothesized that Vanguard has a lower rate of return. We are just looking for a different rate of return, so that makes it two-tailed. All right, the null hypothesis is always that there's no significant difference between the two groups, the two means, or that they are equal. The alternative is the research hypothesis. Again, ours is two-tailed. We're looking for a difference, so we are going to choose the hypothesis that has the unequal sign, right? It doesn't have a direction greater than or less than, and that's because we're considering both. When we do these tests, we are going to use the distribution of sample means. So sample means are normally distributed, so we can see the likelihood of obtaining our sample mean, and then we can evaluate that and determine if we're going to reject or fail to reject the null hypothesis. All right, the historical average is the population mean, and that was provided in the research description. That is 8.6%, and the population standard deviation is 1.7%. For our sample mean at Vanguard, we'll use the average function to analyze the data. And I got a sample mean of 9.0. And let's see what our sample size is. So how many accounts is that based on? And it looks, oops, I actually accidentally have an S in there. We just want count. 100. So we have 100 accounts at Vanguard and they had a sample mean of 9%. Next, we can compute our standard error. This is the sampling error. So this is going to tell us, okay, if Vanguard's mean is really 8.6%, this is the expected variation that we would observe in a sample mean. So to compute the standard error or the sampling error, it is the population standard deviation divided by the square root of the sample size. And I got 0.2%. So on average, sample means are going to be about 0.2% away from this 8.6%. All right, so now we can start to conduct our hypothesis test. So the significance level of our alpha is 0.05 or 5%. And we are conducting a two-tailed test. So that means we have a lower or a left critical value as well as an upper or a right, right? We're doing a two-tailed test. We don't know if Vanguard accounts are lower than the market average or higher than the market average. We're going to explore both possibilities. So since we're doing a two-tailed test, we need to take that alpha and divide it into two. So we're going to split alpha into our two tails, the left tail and the right tail. So now what we're going to do here is we are going to determine the standardized score or the z-score that's associated with the bottom and the top 2.5% or alpha. So that's the norm.s.inv function. And for the left, you just take your alpha, negative 1.96. And then for the upper, we're going to do 1 minus alpha. And you'll notice that our critical values are the same. The lower is just negative and the upper is positive. And this is always going to be the case with a two-tailed test. So this is one way that you can check for errors. All right, what are the cutoffs or the critical values in raw units? So to determine that, you take the population mean plus the standard error times the z-score. Got 8.3%. Now what about the upper? Again, it's the population mean plus the standard error times the z-score. And here are my cutoffs in raw units. So if our mean is below 8.3%, we'll say Vanguard is less than the historic average. If we observe a sample mean greater than 8.9, then we'll say Vanguard is higher than the historical average. And this is what it is in terms of z-scores or standardized critical values. We have a critical value of negative 1.96 and positive 1.96. So what we can do is we can mark this on our charts. So what you can do is you can just take these lines and you can move them. So again, ours was negative 1.96. So that would be, oops, we want to move the line too. So make sure you're clicked on the line. So negative 1.96. And I'm going to grab this one over here, positive 1.96. So these are our critical values and they cut off our rejection region. Now you can see here, this is not a dynamic chart. So the reason why is because we want you to do it on your own so you understand where the critical values fall and how to evaluate the null hypothesis, which is what we're going to do now, right? We are going to determine our test statistic. So we have our sample mean. So you can see our sample mean is 9%. That is above our upper critical value of 8.9%. But let's compare standardized scores. So to compute the standardized test statistic or the z-score for the sample mean, you want to start your parenthesis, and then we do sample mean minus the population mean, close your parenthesis, and then we divide by the standard error. And I got 2.51. All right, so let's plot our test statistic. It is 2.51. So I'm going to take it here, 2.51 right here. And then once you plot the critical values in the test statistic, you can type in the hidden word. So ours is hello. All right, so you can see that our test statistic falls in the rejection region. So we are going to reject the null hypothesis. And we are going to conclude that Vanguard is greater than the historical average, right? Because it's in the right tail. All right, so now computing the p-value for the test statistic or the probability. So when it comes to a two-tailed test, you have to determine, are you going to compute the left p-value, which would be just the norm.s.dist function, or are you going to compute the right p-value? And that would be 1 minus norm.s.dist. So the easiest way to make that decision is to look at your test statistic and determine what area would you need to compute. Do you want to compute to the left of the test statistic, or do you want to compute to the right to the test statistic? We want to compute the area to the right, right? That's going to give us the tail, and that's what we want. We want the area of the tail. So we are going to do 1 minus norm.s.dist, and then we're going to take our test statistic and then true. If you get confused on whether you should do the left p-value or the right p-value for a two-tailed test, you're going to compute whatever one is smaller. So you could always compute both, and then you'll go with the one that's smaller. Now, this is in contrast to a left-tailed test. With a left-tailed test, you just always do a left p-value. When you have a right-tailed test, you always compute the right p-value. The difficulty is with a two-tailed test. So with a two-tailed test for the p-value, you don't know whether you're going to do left or right. One way is to just plot everything out and then look to see, do I want to compare the area to the left or to the right? But it's always going to be the smaller of the two. All right, I got 0.6. So you can see from all of these approaches, we are going to reject the null hypothesis. So it's very unlikely that we would observe a sample mean in this tail. Actually, there's a less than a 1% chance that we would observe a sample mean in this tail. So we are taking that as evidence that we are going to reject the null hypothesis. The null hypothesis is not accurate. Vanguard is not the same as the historical average. We believe that Vanguard is greater than. All right, so let's answer these questions. So we want to reference the p-value. Our p-value was 0.6. What alpha did we use in the p-value approach? We used 2.5%. Right? I'm not gonna reference the alpha for the entire test, and that's because we had to divide it into the two tails because we did a two-tailed test. So we actually compared our p-value to 2.5%, and it is less than alpha. Our p-value is less than alpha, so that means we are going to reject the null. Remember, when the p is low, the null must go. So we are going to reject the null hypothesis. All right, what about the critical value approach? So what is our test statistic? Our test statistic is 2.51, and that is a z-score. All right, what were our critical values? The lower critical value was negative 1.96. The upper critical value was positive 1.96. And our test statistic fell in the rejection region, right? It was beyond the critical value, right? It was farther out on the tail or beyond. And when that happens, we are going to reject the null hypothesis, right? Our test statistic fell in that rejection region. All right, so again, the purpose of the test is to determine if the populations have different averages. We do not know the population mean for Vanguard. We just had a sample of 100 accounts. Obviously, there's way more than 100 Roth IRA accounts at Vanguard, but we just used 100 to make a conclusion about Vanguard's population mean. And we found that Vanguard's mean is significantly greater than the historical average. So in words, it is significantly more. And again, we know it's significantly more because our test statistic, which represents our sample mean, is in the right tail or greater than. Also, just going back and looking at the means, Vanguard is significantly higher than the historical average. So the test is telling us that this difference that we observed is much greater than what we would expect from sampling error, and it suggests a true difference between Vanguard and the historical average. And again, this is inferential statistics, so we are generalizing beyond the sample to the population. All right, the last thing we want to do is we want to estimate Vanguard population mean. So we know that it's significantly different. We know it's significantly higher, but by how much? So we know the sample mean is 9%, but that's just based on 100 accounts. There's way more than 100 accounts at Vanguard. So what we're going to do with our confidence interval is we are going to estimate the population mean for Vanguard for all Roth IRA accounts. So first we got to do the margin of error. So that is the critical value for a two-tailed test, which is our norm.s.inv function. And then that's 1 minus alpha divided by 2. close your parenthesis, and then we're going to multiply that by our standard error. And then the lower is the sample mean minus margin of error. And then the upper is the sample mean plus margin of error. So we are 95% confident that Vanguard's population mean is between 8.7% and 9.4%. And you can see that our range does not include 8.6%, the historical average. And that's why we concluded that it's greater than. So our estimation does not include the population mean for the historical average. All right, so that is it for the IRA tab.